Okay, so today we're going to look at our first algorithm that involves what's known as unsupervised learning. So let me set the stage for this by saying, okay, suppose that we have two-dimensional feature vectors, okay, and we have that we don't know the labels. So notice I'm not giving these any color. I'm just saying that we have the features, okay? We don't know the labels, but we want to group these data points into groups with similar, subgroups with similar features. So for example, I see that there might be a group here, and there might be another group there, right? But we don't know, right? So the way that we can do this is with what's called clustering. And the most famous of these algorithms is known as the k-means clustering algorithm. Okay, so this is a unsupervised learning algorithm, meaning that our input is a collection of feature vectors with no corresponding label. Okay, so let's go ahead and write that down. So we have x1 through dot 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 through xn unlabeled feature vectors. Okay. And our goal is to group, so I'll call this data set X, group the vectors in X according to similar features. That's our goal in unsupervised learning. So the way that we're going to do this is by, we're going to initialize say C1 through CK, randomly chosen centroids. Okay. And the choice of K is to be determined. So we'll talk about that in a bit. Okay. So we have centroids that are going to, in a sense, walk around our feature space and try to find the centers of clusters. So for example, if we take K to be 2 in this case, then we can say that, okay, I'm going to put a centroid right there, and then I'll randomly put another one, maybe like right there. Okay? So after we initialize, so the actual algorithm now consists of, first, we're going to calculate the Euclidean distance from each feature vector to each centroid. Okay, so that's part one here. So it looks like, so we'll calculate the distance here, there, for each of those, right? So then, after we calculate that distance, part two is we're going to assign to each feature vector the centroid that is closest. So the way that this is going to work is that, if feature vector I was assigned centroid Cj, then the current label of feature vector I is j. So in this instance here, it looks like this will be assigned blue, 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 and where's my green? And it looks like this will be assigned green, green. That one's close. It's probably green. And now it looks like it could also be blue. Maybe this one has been assigned blue. Like it's closer to that one than the green one. Okay. Okay. So now that each feature vector has been assigned a centroid, right? We have clusters. So we're going to say let Si be the set of all feature vectors assigned to centroid Ci. Okay, so if blue corresponds to 1, and then green corresponds to 2, so C1 and C2, then S1 would be the collection of all blue points at this point, and S2 would be the collection of all green points. All right? So now, what do? So part 3, the next update the centroids in C. So I'll call this C is the collection of those centroids by the following equation. So we're going to say centroid C I entry J. So note that CI is a vector. In this case, it's a two-dimensional vector. This is going to be equal to 1 divided by the magnitude of CI times the sum, where X is going to belong to SI, times XJ. So what this is doing is it's calculating the mean entries, right? So SI are all the points corresponding to centroid CI. So 1 over the number of those points times the sum of the entries of the J component. So we're just taking the mean of each of the entries in that cluster. So maybe I should just write that down. So this is the mean along the jth dimension. So the mean along the jth dimension for cluster I. So along each of the entries in your vector, you update that entry according to take the mean on that dimension for all the points in that cluster. Okay. So you do this, so I guess like step 4 would be to do this until you reach some type of stopping criteria. What we're going to do is we're going to say that, so this is the initialized phase. It looks like if we take the mean of all those points, so the blue, so cluster 1's mean might go like right here. And then if we take the mean of these 3 here, it looks like we get something right there. And then after we do that, we go back to 1 and repeat. So then it looks like now this will be signed blue, 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 but now after we've updated the centroids, it looks like this is green, that's green, that's green, and that's green. Okay. So then we would repeat. And if we ever get to a point where our centroids stop moving, it means that we've kind of nestled into a cluster of points. And then at that point, we can say that these points here belong to cluster 1, and these points here belong to cluster 2. Okay? So now let's go ahead and look at what it's like to code this. So again, when I'm coding these things from scratch, it's not necessarily the best way to code it. It's just the way that I chose to do it. And it changes every time I do this. So keep that in mind when you're looking at my code here. Okay, so I have a short description here and some issues with unsupervised learning. I've kind of already described this business up here. So there are several issues with unsupervised learning, but we're able to work around them in most cases. I described what clustering was already, so I'm going to go ahead and just start running some code now. Okay, so I should probably start describing what I'm doing here. So I'm artificially creating clusters inside of a circle. So here I have len range of values between 0 and we have 0, 2 pi, and then 500. And then I just pass in how you would define a circle. So the x value is that, and y value is this. Okay. So then for my cluster 1, I just kind of randomly assign points. Okay. And that's all I'm doing here is I'm just randomly assigning points that fall within a circle. And then if I plot this, and there's many different ways to design your own artificial data. This is just how I ended up doing it. It's going to take a moment to run.
By circle, do you mean that you're assigning a centroid?
No. This is nothing with k-means right now. This is just me getting some data. I'm artificially generating data that happen to lie in a circle of radius. Radius r. Okay, so all right. So I've generated some artificial data that now I want to try to run a clustering algorithm on. Now here I just have code to kind of plot the data. Okay, so it's roughly kind of centered around there, roughly kind of centered around there. So I've artificially made this data, and I see that there's these two clusters here, and I want to run k-means on this data to try to find the clusters myself. Like supposing I didn't know that they were in clusters, here is an example of what the clusters might look like. Okay, so in order to do this, we need the Euclidean distance, which is this simple function here. We call it just the square root of the sum of different squares, the difference of squares. Okay, so first, we need to calculate the distances from the points, from each point in our training vector, to our centroids, and we have to choose how many centroids there are. Okay, so the way that I did this, and it might seem kind of funny, but I just made a dictionary of dictionaries. Okay, so what goes inside this dictionary? Well, start with an empty dictionary, and then for each point in my collection of feature vectors, I make another dictionary, right? So a temporary one. And then for I is equal 1 to k, so the number of centroids, I say that the temporary dictionary with key I, right? So that's centroid I is equal to the Euclidean distance between my point, my feature vector, and the centroid. So all I'm saying is that this dictionary with key I is the distance from P to centroid I, and that's for 1 to k. And then after that, I say that this distance dictionary with point P as the key is equal to the temporary dictionary. So what this says is that if I put in a point as my key, then I have that points towards another dictionary where the keys there are the centroids and the key values are the distances. Oh, I need this first. Okay. So next, I need to assign the clustering, right? So this was part 2 of what I wrote on the board. So the way that I do this is I take in my data set, I take in a collection of centroids in my value for k, I find my distances, okay? And then my clusters are going to be dictionaries where the keys in this dictionary are the points, and the key values are what cluster they belong to. So for each point in my feature vector, in my collection of feature vectors, I just say, I do this kind of like haphazardly. I just say, okay, I'm going to assume that that point belongs to cluster 1, and that distance, min d, is the distance from P to cluster 1, or the centroid at 1. Okay? So then for I is equal 2 to k, if the distance from my point to centroid I is less than min d, then I say clusters P is assigned to I. So point P is assigned to cluster I. And then I update my min d to be the distance from my point to centroid I. And I do that for each of the points in X, and then I'm able to assign to each point a cluster. Okay? So now I say that, okay, once I've assigned my clusters, then I need to update my clusters, right? So k-means new centroids here is just a function that does that. So here I get my clusters, and here I'm going to push in my new centers. Okay, so I start with centroids here, and then I'm going to have new centroids here. Okay. So we're dealing with two-dimensional space here. So I just say for j is equal 1 to k, the new x value is going to be the mean of the points, the x values, that's where the 1 is there, the x value for point P in P, for P, and the keys of the clusters, recall the keys are the points, if P has been assigned cluster J, where J is scrolling through 1 to K. That's just the kth centroid, or jth centroid. And then I update my Y values, and I say, this is my new point, and then new centers, I'm going to push that point. Okay? So this is just calculating the mean of each of the entries, just like I wrote on the board. So let's kind of see this work in practice. So here is my data that I generated earlier. So I'm going to initialize some random centroids. So there's 2 of them, so I'm taking k to be 2. I'm just going to say that k is equal to 2. I'm assuming that. I'm going to print that out. And then I'm going to say my clusters are, I'm going to call my k-means clusters on those initial centroids. Plot the points again, and then let's just see what this looks like. So here, the star, that's my initial random centroid. So initial centroid, these random points, that's group 1, that's group 2. Okay? And these points are colored red if they're closest to point 1, and they're colored blue if they're closest to point 2. Oh no, the blue point is point 1, the red point is point 2. That's what the coloring is saying here. Okay. So let's go ahead and say, I'm going to test out my k-means new centroids function. So I'm going to say, I'm going to feed in the initial centroids, and I'm going to get out new ones if my function worked correctly. And then here, I'm going to find my new clusters with my updated centroids. And I'm going to plot the same stuff as before. All right, so see what happened here. These points were assigned with this centroid. So then when you average out all the x values and average out all the y values for this cluster, this centroid is going to move way up here. You see that? It moves right there. And now we see, even after just one iteration of this, that we've clustered our artificial data. But let's go ahead and see what happens if we run this again. I'm just doing the same exact code again, but now I'm feeding in centroids test, and then that's my new centroids test. All right, so did our our centroids move very much? It looked like they did, right? They're always going to be at the mean of the points in that cluster. See how they did move. Okay, so let's try this with let's see what happens when we try to cluster this with k is equal to 3. So now I'm starting with 3 random centroids. Okay, I'd like it to where at least one, okay, good. So at least one is green. These are all the ones that are red. I don't even know where blue is. Blue's probably like over here to the side somewhere. So let's see what happens if we run this again. So green came down here, red came over here, blue's right there. Run this again. And you see that we're slowly starting to cluster these things together. And if we did it again, this would probably end up over here somewhere. And then this one would probably be there. So we have these this little red cluster, this green cluster, and this blue cluster. So the stopping criteria that I choose is that my centroids don't change very much. I also have a maximum number of iterations because I have a while loop, and I just want to make sure that it does stop running at some point. Okay, so this is how I do it. So we have our data set K stopping criteria, and then this is an optional argument here to return the centroids and not the clusters. So centroids is here. So this randomly picks out an integer from 1 to the length of x. This randomly picks out an integer from 1 to the length of x, but then divides by x, so it's just some small number. And I push in the centroids for 1 to k, x of I plus j, and then x of I minus j, so the x and y values. You can, there's many different ways to initialize your centroids, and I'm going to post some things on Blackboard for you to look at. I could put a plus here, I could do any number of things, but this is just how I chose to do it. So now I calculate my new centroids, and I have a counter here, and it says 1. So it says, while the distance, the maximum distance from the centroids to the new centroids, while that is greater than epsilon and my counter hasn't gone too big, I say centroids are my new centroids, and my new centroids I calculate using this. So this is that double assignment, and then I increment my j. So then this if-else statement is just with this optional argument here. So if that's false, then we're going to return the clusters. And if I set that equal to true, then we'll return the new centroids. Okay. So let's run that on the data that we had above. So this is the keys are the points, and the key values are the cluster it's been assigned to. Notice my epsilon I set to 0.001. And then if I want to look at the centroids, I can just do this. So these are the proposed centroids of that that it says. So then we can use that to make predictions on our clusters by just getting the centroids and the clusters. So this point here we predict is class 1. Okay. So let's go ahead and look at how well we did this. There. So we iterated that process up there, and we were able to find these 2 clusters. And if we go back to our original data set that we generated, those were the 2 clusters that we had in mind. So we artificially generated that data, knowing that those 2 were going to be the clusters. And then after running this down here, we see that we did find those clusters. So now let's try with an artificial data set of 3 clusters. So here's my data set consisting of artificial 3 clusters where we have this cluster, and this cluster. And let's see if our algorithm will work on that. So this data new right here is just cluster 1, cluster 2, cluster 3. I just randomly make points all over the place. But I specify that they're close together. So that's kind of how I made it look like clusters here. So I run K-means algorithm on that. And we see that it found those 3 clusters. Okay. Okay, so it's a fairly simple algorithm, but I haven't discussed how to choose your K. And the choice of K is often described in terms of this elbow rule. And I'll post a video on Blackboard describing that rule so that you can see how your choice of K changes with this rule. Okay. Okay, so that is K-means clustering, the gist of it. I'd like for all of you to program this yourself, and then also go out and try to find some data that you can test your code out on. All right. So the K-means clustering algorithm will be the last of the algorithms that we programmed from scratch, completely from scratch. Like everything that we've done so far has been completely from scratch using Julia. Starting next week, we're going to transition to using Python, and we're going to actually use libraries and look at more applied scenarios where we're not coding it by ourselves. We're using the help of these highly optimized libraries that exist. And we will be, well, I will be following this book. Okay, it's a really dense book, but it's got everything you would ever need to know about programming Python for machine learning. And then also the second edition here, I'll be using this as well. Okay. All right, so please, everyone, send me updated links to your GitHub accounts. I'm really curious to see what they're starting to look like. All right, that'll be it for today, and I will see you next week. And we will be starting Python then.
Thank you, Dr.